going to start today by looking at this table here. So if we think back to our other videos when we started with the table, we looked at any patterns we saw happening as x and y were changing. So if we look at this table, what do we have to add to 1/3 to get to 1, right? That's what we did on our other tables. We figured out what is the pattern when I add the same thing every time or subtract. So here, if I do 1/3 plus 2/3, I'll get 1. Okay. Then what do I have to add to get 3? 1 plus 2 gives me 3. Okay. So those are not the same. And then 3 plus 6 gives me 9. Those are all not the same number, right? So this is not growing by a constant number every single time, right? So this is not a linear function. Okay. So let's see if we can notice any other patterns in this table. Okay. So if we look at 1/3, what do we have to multiply 1/3 by to get 1? Okay. Well, if I multiply 1/3 by 3, I can get 1. Okay. And then if I multiply 1 times 3, I can get 3. And then 3 times 3 gives me 9. And then 9 times 3 gives me 27. So this growth is called exponential growth or a geometric pattern, right? It's different than adding because we're not adding the same number every time, but we're multiplying by the same number every time. So when we graph this, it's not going to be linear. Okay. Let's graph it so we can see what shape this type of function makes. So if you see over here, this graph is a rough sketch of these points. So we can see it's not linear, doesn't create a straight line like our other tables did, but it creates an exponential function. Okay, so this grows exponentially, and we'll talk more about what that means.
All right, let's see on the graph where maybe parts of our table show up. So we see here that this is at 1/3, and we go up to 1. So right now, if I make a slope triangle here, this is a difference of 2/3, right? We were talking about our differences earlier. If I go to the next one here, I made a slope triangle between these 2 points, between 1, 1 and 2, 3. I see that I have a difference of 2, a height of 2. Okay, what if I did the next slope triangle from 2, 3 and 3, 9? I see that my difference in height is now 6. And if I did my next one between 3, 9 and 4, 27, that is a difference of 18 here. And so we can kind of see how our slope triangle is changing, right? On a linear graph, our slope triangles are equal every time, right? Steady, it's growing at the same rate every time. However, with an exponential growth or geometric growth, we can see that our rise or our slope triangle, it's getting taller every time. And it's actually getting taller by that times 3 factor that we saw earlier, right? 2/3 times 3 is 2. 2 times 3 is 6. 6 times 3 is 18. If I did the next one times 3, I know that my next slope triangle would be a height of 54 because that will be our next difference. All right, let's check out this example here with this table. We got 0, -6, 1, 48, 2, 24, 3, 12, and 4, 6. Let's see how much we are decreasing by to get from one number to next. So 96 to 48, that's a difference of 48. And 48 down to 24 is a difference of 24, 12, and then 6. Okay, so this is not a linear pattern because we are not decreasing by a constant rate. But we do see that it is kind of repeating itself, right? Like 48, 24, 12, 6. So another way we could look at that is that it is being divided by 2, right? 96 cut in half is 48. 48 cut in half or divided by 2 is 24. 24 cut in half is 12, and 12 cut in half is 6. So our pattern here is that we are dividing by 2. We are decreasing this time. Remember that dividing by 2 is the same as multiplying by a half. So if I were to type in my calculator 96 divided by 2, that is the same thing as if I did 96 times 1/2. And so dividing by 2 is the same as multiplying by half. And so this is what we call our common ratio. So our common ratio is whatever number we are multiplying by to get to the next term. In the last video that Emma showed with us, our common ratio was 3 because we are multiplying by 3 every time. In this case, our common ratio is 1/2 because we are dividing by 2 every time, or we're multiplying by a half every time. Let's look at our graph here. If we were to do a rough sketch of the graph, we can see that it's not linear, right? It's not a straight line. It's just a nice kind of swooped downward thing going on, which is what we call exponential decay because we are decreasing our amount each time. If we were to draw slope triangles here, we can see that our y values of our slope triangles get cut in half every time, right? Like originally this is a distance of 48, then jumps down to 24, then it's halved again to 12, and then 6, and then 3, and then it'll keep shrinking down.
All right, so another way that we can represent exponential growth or a geometric pattern is through a sequence, and that's what this is. A sequence is a list of numbers, and from a sequence, we can figure out what the common ratio is, meaning we can figure out what am I multiplying each term by to get to the next term. And a lot of times in sequences, they label the terms as a sub 1, a sub 2, so this would be a sub 1. This term would be a sub 2, and this term would be a sub 3. So if you ever see something like this, that's just how terms within a sequence are labeled. So if we're looking at this specific sequence here, we have to see if we can figure out, just like we did with the table, how did I get from term 1 or a sub 1 to a sub 2? What do I have to multiply by? And then what do I have to multiply by my term 2 to get my term 3, and so forth. So if we look at the first one, what do I have to multiply 1 by to get -4? Well, I know that 1 times 4 gives me +4, but if I want this to be a -4, that means I have to multiply this by -4, okay? If this is a geometric sequence, it means I have to multiply by the same thing every time. So let's check to see if this works for all of these numbers. So if I then take -4 and I multiply it by -4, I do get +16. So that's awesome, okay? And then let's try it again. So +16, multiply that by -4, I get a -64. And then whenever you have an alternating sequence, it means we're going to have to multiply by a negative number, because a positive number times a negative number will give me a negative number. A negative number times a negative number will give me a positive number, and that's what gives me that alternating effect in my sequence. So on your derivative assignments, you may be asked to find the common ratio given a sequence. So we would say that the common ratio of this sequence is -4. And a lot of times the common ratio is written as r. So in this case, r is equal to -4. Every time I move on to the next term, I'm multiplying by -4.
Let's check out this sequence here. We got 1, -1/3, 1/9, -1/27, and 1/81. Okay, this looks a little bit crazy, but no worries, it's gonna be all right. So we got a sub 1, this is our first term. A sub 2, this is our second term. A sub 5. Okay, just like Emma mentioned in the last one, notice that our signs are alternating, right? We have a positive, negative, positive, etc. So we know the next one, a sub 6, will have to be a negative option. So we know that right off the bat, our ratio is gonna be multiplied by negative. So when I take this number and I multiply by negative, I'm gonna get negative. Take it, get a positive. Now we want to find our common ratio, and this is the number we multiply by each time. Some of us are really savvy and we know that, oh, 1 times anything is just itself, so I know my common ratio is -1/3, because 1 times -1/3 will give me -1/3. If I multiply this by -1/3, then I get +1/9. If some of us aren't as comfortable with fractions or with multiplying, there's another trick that you can do to help you find the common ratio. And this is actually why it's called a ratio, because a ratio means you're dividing two things. And so you can take any two terms next to each other and you can divide the larger term by the smaller term, and that will tell you what your common ratio is. So let's do it with a sub 5 and a sub 4. If I have two numbers right next to each other, I can divide them to find my ratio. So my common ratio is equal to my term that's larger, so the fifth term is 1/81. If I divide it by -1/27, you can type that in your calculator, you just have to be careful with your grouping. You'll have to do like parentheses 1/81 divided by parentheses -1/27. You could type it in like that, or you could also remember our rule: when we divide by a fraction, that is the same as multiplying by its reciprocal. So I could take 1/81 divided by -1/27, and that is the same as 1/81 times -27/1. And then if I multiply across 27 and over 81, and that simplifies down to -1/3. So that's another way you can find the ratio if you are unsure what the pattern is. You can take any two terms next to each other, what we call consecutive terms. We'll take the larger term and divide it by the smaller term, and that will also give us our common ratio.
All right, so something else that you guys are going to see on your derivative assignments is being able to create the sequence by listing. It's usually going to ask you to list the first 4 or maybe 5 terms when you're given a sub 1, which is our first term, and the common ratio. So if we know our first term, a sub 1, is 2, we already know that's going to be our first term. That's easy to write. And then we can use this common ratio to figure out what the next terms are going to be. And again, remember, the common ratio is what we're multiplying by each time. So that means that we are multiplying each term by 4. So if my first term, a sub 1, is 2, then my next term, a sub 2, will be 2 times 4, my common ratio. So 2 times 4 is 8, okay? And then a sub 3, we need to get all the way up to a sub 4, okay? So I have 2, and then 8, and then 8 times 4 is 32, and then 32 times 4 is 128, okay? And then you can keep going if you wanted to, but most cases they're going to ask you for the first 4 terms. All right, so what if they don't give you a sub 1, but they give you a different term, and they still ask you to find the first 4 terms? So we can have a sub 1 and a sub 4. Okay, we already know a sub 3, so that's awesome. Right here, we know that that's 24. And we know that our common ratio is a -3. Okay, so if we have a positive 24 here and we want to find our fourth term, then we can just say 24 times -3, which will be a -72, because we know that a positive times a negative is going to give me a negative. Okay, so then because of this negative here, we know that this is going to be an alternating pattern. So we know that our a sub 2 has to be a negative. If we're going backwards, okay, we know that that this number multiplied by negative 3 has to give me positive 24. So there's a couple different ways you can think about it. Think in your mind, okay, what number times 3 is going to give me 24? Okay, well, I know that 8 times 3 gives me 24, but I need it to be a positive 24. So this means that this would have to be a negative 8 times a negative 3 gives me positive 24. Or you can go backwards by, instead of multiplying by negative 3, you can divide by negative 3. Okay? So when you're going forwards, you're multiplying by negative 3. When you're going backwards, you're dividing by negative 3. So 24 divided by negative 3 gives me a negative 8. And then if we do that same pattern here, divide by a negative 3, a negative 8 divided by a negative 3 is going to give me positive 8 over 3. And we can just leave it as a fraction like that. So if we aren't given the first term, but some term in the middle, we can use this common ratio to work forwards and to work backwards.